Our first speaker this morning is Dr. Glen Brown. He's a research scientist with the Ontario Ministry of Natural Resources and Forestry and an adjunct professor at Trent University. Not Lakehead, that's good. We spread it around. He has worked for both government and industry to develop monitoring programs and conduct research on wildlife that inhabits managed forests. His current research aims to improve the understanding of the effects of climate change and other human factors on ecosystem dynamics and wildlife that inhabit the Hudson Bay lowlands. That would include polar bears, and there's some walruses just off the shoreline there, so he's got a whole armful of things to chase down. Lisa Polic is a wildlife biologist with Wildlife Research and Monitoring Section of OMNR and Forestry in Peterborough over the past 3 years, working with MRNF. She has completed various contracts ranging from waterfowl to rabies to black bears and wildlife habitat monitoring in Ontario managed forests. She obtained an honors degree with wildlife biology from the University of Guelph and an MSc from Trent, focused on shorebird ecology and conservation in the subarctic. She's worked in both the private and public sector, primarily focused on avian conservation. So there's your hit team for this morning. Guys, it's all yours.
Do that. Okay, so yeah, before I jump into the main details of the project, I do want to give some credit to some other players who aren't here who've been contributing substantially. Samantha Cava is a master's student based at Trent with us, so she's funded through the FFT, and she's working on the indicator identification question. She couldn't make it though. Ian, Dennis, and Kyle, again, funded under the FFT funding envelope, and they've contributed substantially to data assembly, putting all that FRI together for those separate SFLs into these big habitat mosaics across the province. And then the Wildlife Monitoring Program data we'll get into. There's a lot of work went into developing that program. Neil Dawson and Dean Phoenix were key players, and more recently Phil DeWitt. So just for background, to get going, when it comes to wildlife and forest management, we don't manage the wildlife populations directly. We manage their habitat with the assumption that if we build it, they will come, right? So historically, back in the day, we had a pile of individual species guides in forest management planning, like for moose, the moose guide, the pileated woodpecker guide, the deer guide. And so there was targets for a mountain arrangement of habitat for each of those species, and it was kind of complicated and onerous. And so we switched over now to the more recent landscape guide and stand and site guide process. And within that, the targets for a mountain arrangement of habitat aren't wildlife habitat specifically, they're just the range of forest conditions that we assume are present under a fire disturbance model. But models are models, right? And so there's uncertainty there. Did we get it right? Is the model adequate to describe the range of conditions? And we know it's not. Models are simplifications of the real world. And so the uncertainty is, through all of our best efforts to maintain biodiversity, are we effective, right, at sustaining wildlife? So with that as one objective of sustainable forest management, of course. So with that uncertainty in mind, that's what kind of spawned the Wildlife Population Monitoring Program, as it's called. So under the environmental assessment conditions, condition 30 in this case is what it was originally called, the MOE set out, well, if you're going to do forestry on crown land, you need as one indicator to sustain wildlife or demonstrate that you are. So the Wildlife Population Monitoring Program was born, and their job was to collect information on status and trends in terrestrial vertebrates only across the area of undertaking of forest management. And so my past life before I came to my current job was to help develop that monitoring program. And so one of the things we saw there as a need was not only to track changes in wildlife, but if you really want to more strengthen that relationship of your monitoring program to management decision making in terms of forest management planning, we really need to be tracking targets in wildlife population indices and habitat response. So part of it is, did we get it right when we set these targets for forest condition? Did we create the habitat we thought we would? And are wildlife responding in concert? So that's what we needed for forest management planning and to make our monitoring program useful. So when this proposal from FFT came along, it seemed like a great opportunity to me to better integrate things like the FRI. That's like the main data set that we can use to characterize habitat within FMPs, right? But we know that it's not perfect. It's not designed for wildlife, so there's a lot of uncertainty, and wildlife don't just use forest vegetation features. They're affected, their distributions and population response is affected by a suite of things that we don't monitor directly. So part of what we want to do here in using the FRI was start off by asking these kinds of questions. Can we better integrate FRI and that wildlife program data to inform forest management planning? So the first step in that is take your FRI and say, well, how well does that actually characterize what we think is wildlife habitat in terms of forest vegetation condition, step one. And then from there move into describing the wildlife habitat relationship. So for each of these species, what do they respond to in forest condition? And then taking that collective information, so the last two bullets there, it's really then identifying the best suite of indicators. So within the forest management guide process now, we do have evaluative indicator species, but we saw a good opportunity here with this new monitoring program, as I'll get into and show you, to derive our indices and our best monitoring species from that monitoring program data itself, as opposed to a bunch of one-off studies in localized areas of the province that may not reflect the broader picture that the monitoring program is meant to represent. So it was a great opportunity, right? So for the first part, so back in a few years ago now, I think it was 2013 we started, we implemented what's called multiple species inventory and monitoring protocols within the wildlife assessment program. And so the beauty of these, they're borrowed from the US Fish and Wildlife Service approach to doing broad-scale monitoring. We used a standardized set of protocols for a wide range of terrestrial vertebrates at permanent plots, and it gave us core scale information. So the trade-off is you're not getting vital rates from this monitoring data. You're getting species occupancy, presence, absence, as well as relative abundance for a lot of these protocols. And it's at a broad landscape scale. So, our mandate was really to make sure that our monitoring covered the entire area of undertaking of forest management. So what we did, and to better integrate with kind of the forest inventory program, we took a random sample, a spatially balanced random sample of the NFI grid points, because there's other data collected there that we can use for our program. There's a lot of interest there in gaining efficiency, right, where we may not have to collect the same level of habitat information ourselves directly within the wildlife monitoring program by doing it this way. So the data we'll talk about today, we just have 1 year of data for across those green dots. So it's 146 plots across that area, which is, at face value is quite a nice data set to work with for this. So if you drill into each of those sites, this is the way they look on the ground, right? We have 5 cameras set up, 500 meters apart approximately, to get presence and absence of medium to large mammals. We have 3 song meters, get forest calling songbirds, 3 small mammal trap lines, and a salamander cover boards. Another thing we debated early on, and we decided to go ahead and collect, much to probably the chagrin of some of the field crews. I was making them count detailed stem counts through the thick bush. I think they hated me for that. But we felt early on that it was important, not to just rely on the FRI, but to collect habitat information right at the site where we're getting our wildlife data to strengthen our inference, our ability to understand wildlife habitat relationships, right? So we didn't want to assume the FRI would be good. We wanted to get the ground data first with all that detailed vegetation structure from the ground up to the canopy, and then compare it to the FRI and move on forward from there with decisions as to what to measure in the long term. So back to this first question under the FFT project, how well does the enhanced FRI characterize forest structure that we think is relevant to wildlife? So for that, what we did, so the diagram on the left there, you guys don't see the mouse when I use it, eh? So the diagram on the left with the trees, that kind of represents where we characterize vegetation structure on the ground at our MSIM wildlife sites throughout these several vertical strata there. So we have this detailed information, and then on the right, these enhanced variables. A caveat for this comparison is that at the time we assembled all this data under the project, only those SFLs you see there had those enhanced attributes available to us. And within those, there was a lot of gaps across SFLs as well in terms of those understory enhanced attributes. So we used the understory crown closure variable, that's UCC there, the vertical and horizontal ones, which each have 7 or 8 classes. And so the way we did this to understand how well those FRI enhanced variables could explain our ground data, we put it into an ordination space basically. So the way it works, you take your FRI variables, these understory ones, and you use them as the constraining variables in an ordination, and they're used to explain the variation you observe in your ground data and the real conditions at the site where we're collecting our wildlife and habitat data. And so then you take all that data in a multivariate environment, put it in this ordination space, and these are just the 2 first ordination axes. And so what you see up there, those red arrows represent the locations of the habitat variables we collected on the ground, and the blue arrows are the FRI variables. And so we're blue and red are close together, those arrows, they're highly correlated, which suggests there's an association there. So the good news from the ordination was that these relationships are meaningful. Like down in the bottom left corner where you see the hardwood greater than 2 meters, that suggests that in these FRI-based stands where you have a vertical two-tiered canopy structure, it's also associated from our ground data and consistent with a stand where you have a lot of hardwood in the understory, suggesting more complexity. So the relationships are meaningful, but for those of you who are looking at that R squared, it's quite dreadful, right? It suggests that 0.1 there says that only 10% of the variation in our ground data could be explained by these understory variables, which, yeah, it was kind of disappointing on the first run when I saw that. But so we were stubborn, though. We didn't let that stop us. We didn't give up, and there's more to be learned from the data beyond just those low numbers. The next stage, so with this first ordination, you use the understory variables, but then we decided, well, okay, let's go back to just a classic FRI variables, so things like species comp, age, height, stocking, and see how well they explain and describe our understory data from the ground. And you see the improvement there, right? It does. The explanatory power goes up to 15%. It's not huge, but there's an improvement there, and the relationships are meaningful based on that ordination space there. So looking at it a different way, when you put them as kind of these circular plots, you see, the independent and shared power is what's represented here of these FRI variables to explain the data on the ground. So although it's low, we see, there's twice as much of that variation in the ground data that's explained by the overstory variables than the understory, which is a little contradictory. We would have thought that those enhanced variables, which are more directly related to the understory features we measured, would do a better job than the overstory, but they didn't. But the take-home message here is that both are relevant and useful, right? So we can improve our overall ability to predict understory habitat features using both those enhanced and the classic FRI variables with a lot of residual unexplained variation. Again, we were stubborn. We kept going with this. So the next step was I wanted to take the bird community data and getting back to this idea of do we need to keep collecting vegetation data on the ground? It's costly to have crews out there, right? So for this, it was a similar kind of ordination process. We take the ground data, forgetting about FRI, and ordinate it against the bird community data, and then we take the FRI and do the same thing. So in this first ordination plot, no FRIs, just using our ground habitat data to characterize the variation among sites in bird relative abundance in the whole bird community. And you see, the explanatory power, the R squared goes up to 0.2. It's not amazing, but it's higher, which you would expect, and it's a significant ordination. Then you just forget about the ground data and use FRI, and you see it's lower, which is not surprising. It's intuitive that if we're out on a site right at the ground where a bird is selected to build its nest, surely we can do a better job than a remote sensing-based approach, to characterize the vegetation. So the ground data did better, but likewise here, the take-home message to us was both are important. So we're not going to get everything we want to know about habitat for wildlife just using FRI, but yet it has some independent contribution to explain. So it suggests that some ground data collection and FRI together are probably going to be better for us in that program. So yeah, with all that in mind, the next part of it, Lisa is going to talk about what forest conditions affect wildlife. Just looking, so when you drill down, a point that I will make, right? So these, all that low explanatory power, one thing you have to keep in mind with an ordination here is that it's focused in on the variation across sites in the bird community at large. Whereas if you drill down, you forget about all that complexity and you just look at individual species and its associations with wildlife, you get much more informative models, and we can learn a lot more using the FRI and the ground data than those low numbers would convey. So you go, Lisa.
Okay, so as Glenn mentioned, we wanted to use the FRI imagery to measure habitat variables and relate these to wildlife occurrence or relative abundance. So in order to do this, we combined the 41 forest management units using consistent classification across all the FMUs. And so this took a lot of work, but eventually produced a continuous raster layer, as you can see a picture there, across the entire province of each variable updated to 2015. And this produced 24 different categories of forest type as well as seral age combinations. So in addition to the habitat or the forest habitat type, we also included continuous forest age variable as well as non-forest habitat where appropriate in our wildlife models. So we also wanted to examine other variables such as climate, because this may impact wildlife habitat relationships. So we examined and analyzed 5 different climate variables, including average temperature in the summer and winter, as well as precipitation and start of growing season. And we also obtained a snow depth index layer and calculated annual as well as an 18-year average snow depth. So disturbance also may play a role in wildlife habitat relationships. So we examined different disturbance variables, including harvest within the last 10 and 20 years, forest fire within the last 10 and 20 years, and as well as distance to roads within or from our study plots. So in order to examine the habitat features wildlife are selecting at both a local and landscape scale, we created buffers around each of our study plots at various distances in order to account for different wildlife home range sizes. And so, yeah, at the plot level, as well as you saw earlier, the 3 bird stations. So we created buffers around each of those and then performed zonal stats within each of those buffers to calculate the proportion of habitat of all the variables I mentioned before in those buffers. So forest patch metric measurements also may play a role in wildlife habitat relationships. So we calculated the amount of total edge, the ratio of edge to area, and also continuity using frag stats, and used the combination you see above, the forest type and the age classes. So in order to examine these relationships, we use hierarchical modeling approach. So we started either with, as I mentioned, presence absence or relative abundance measure. And then we wanted to test the importance of these 6 hypothesis-driven variables. So we built different food, climate, disturbance, forest structure, age, and forest type models. And use certain variables depending on each species' habitat requirements. So we wanted to test forestry variables as well as other habitat variables that we measured. So then we combined all the 6 different model types to make one overall best model using AIC selection. Let's give you a couple examples. So first we'll start with one of our large mammals, the lynx, because basically they're pretty. So since lynx are so tightly associated with their prey species, the snowshoe hare, we also wanted to calculate a food index. So we calculated the number of hare based on how many days it was visible on our remote cameras at each plot during our study period. And as you can see, our model reflects the importance of hare as it was the strongest relationship. But also you can see that the FRI variables do a pretty good job of modeling lynx, which makes sense because they have such a large home range that you would think a larger scale variables would be more relevant to the species. But then when you look at something like a redback vole, which is a small mammal, you see that our ground data that we collected turn out to be more important for the species habitat requirements. As you can see, there's only one FRI derived variable in there. So the forest floor structure is more important, which makes sense because they rely a lot on coarse woody debris and leaf litter for shelter. So this summarizes all our mammal models. It's kind of messy, I know, but basically you just have to look at, so the large mammals are on the top, small mammals are on the bottom. The color of arrows, so the blue ones are FRI derived variables, the green are ground data. So you can see there's quite a mixture for all the different species. Oh yeah, and the arrow size, the thickness represents the size of the parameter estimate. And this gives you an idea of which types of variables were in our final models for all the species. So you can see that forest harvest at various stages, as well as different forest metrics being the most prominent for mammal species. And then jumping over to an example from the bird world, we use the ovenbird. So they're known as an indicator of mature hardwood forest. And as you can see on your right, they're declining in Ontario. However, we found that our ground data, it was a purely ground data model. So there was a stronger relationship with our ground data compared to our FRI. We did find a positive correlation with hardwood forest, but a stronger one relating to, as you can see, tree height and species richness, which is more of an forest age. And again, a similar diagram for the birds. These 7 species represent a wide range of forest conditions that are managed in Ontario. So again, you can see a mixture of FRI and ground data produce the strongest models. And again, a summary of the most frequent habitat variables in our bird models split into ground nesting, tree and shrub nester, as well as cavity. This is just the 7 species you saw previously. So you can see if you look at the tree nesters, it's good that a lot of tree variables are in there, so it makes sense with their biology. Let's give an example. So one of the ground nesters is a black and white warbler, and they prefer hardwood, but we found that having an interaction with hardwood and moss produced a stronger relationship because they pick insects out of moss. So again, the combination of FRI and ground seemed to be stronger. So this is just a summary of the proportion of species that I've discussed today that were both positively or negatively associated with forest harvest, edge, and forest age. So you can see that with more forest harvest, there's fewer, or more species are affected by more harvest. Forest edge, there's more like a more complex, higher edge forest. Some of this is to do with their biology. And then for forest age, there's about half and half species prefer either older or young successional. But again, much of this reflects their individual species requirements. Then if you look at this, it's based on our final models. So the blue are FRI dominant species models, the green ground dominant, and then yellow is mixture. So you can see, again, continuing the theme, the majority, or about half the species, using both FRI and ground variables, improve the habitat relationships. I'll throw it back to Glen.
Thanks, Lisa. So yeah, the last set of questions then is to circle back and take all this information we gained from the habitat modeling and the ordination and get back to, so what are a good suite of indicators, the population parameters and the habitat indices that we want to track through time. And so for that's very much a work in progress. So the indicator question of what makes a good indicator and what are the best suite of indicators for this program is something under Samantha Cava's graduate thesis, which isn't finished yet. So all I'm going to do for today is give just an overview of some of the different approaches. So basically we want to take a methodological approach where we compare these different approaches that have been already out there and compare results and not just pick one and assume it's the best one and that we'll trust in all the results, right? So basically, like a good a good wildlife indicator should be one that's found in the habitat condition you're trying to manage consistently in that habitat and not in a range of others. It shouldn't be a generalist, basically, where it's less sensitive to change in particular forest conditions that you're retaining on the landscape. And another point there, that last bullet, is that they should be easy to count and identify, which I'll come back to around what we collect in our monitoring program. So the first method we're looking at is what I was showing earlier. So I didn't go into it in detail, but you can learn a lot from that ordination space of wildlife habitat associations. And it's something Rob Rimple, a research scientist in M&R, had done several years back, where he took his bird data sets and put them in ordination space. And he hypothesized that the species that are at the edges of these environmental gradients, so the edges of the ordination axes, and then when he translates that into this box environment on the right, you see where these species fall out on the edges of the boxes, on the edge of that environmental gradient. Those are the ones that should be most sensitive to change in forest condition, perhaps brought about through forest management. And the hypothesis there is that we homogenize forests. We get rid of some of that heterogeneity when we grow forests back. And so with that shrinking of habitat space, you may lose some of those species. But it's an untested hypothesis, and I think especially with these ordinations, you have to be careful. What you put in dictates what you get out. And so, if you're doing the ordinations on a smaller set of study areas, you may get a different question than what we might get if we take the whole AOU with our data set and have a broader range of forest conditions that we create this ordination space around. And for us, it's probably more important to do it at that scale because that's the scale at which you do our monitoring to influence management. Back to that, they need to be easy to count. So that's just something we learned, right? The forest guides, they have a pile of evaluative indicator wildlife species in there already. But this helps us fine-tune those species, right? So we found, like those in pink or red there, however it's showing up, we don't see those, we don't detect those with our protocols in enough numbers to really say anything meaningful about. We're not going to be able to track trends through time in those indicator species that are currently listed, or say much about their habitat relationships. Now, some literature suggests, like for example, the palm warbler likes lowland, kind of swampy conifer areas. So, for us now, we can go back with our bigger data set and see, well, do we need to replace the palm warbler? We can't monitor it with our monitoring program anyway. It's not likely we're going to get enough detections at this point. Can we replace it with a different species based on what Samantha finds? Another method is more simple. One she was really keen to investigate. It's quite intuitive, right? It's something Pierre Legendre, one of the kings of ecology and multivariate analysis, came up with. And it involves just taking the count data from your sites and generating this index of a value. So again, it takes into account how often a species is found in a given habitat type relative to all the other habitat types. And so it has a maximum value. So she's exploring this, and just some preliminary results here to suggest, there's some mixed findings with how useful the in-val will be for us. She's finding some meaningful associations. So various things like the ruby crown kinglets are found in mixed conifer lowlands, EMCL, these are the acronyms for the provincial forest types. That's what she was using as a class system. So there's consistency there, but we don't want to just hang our hats on that. We want to compare the different methodologies. And of course, blast from the past here, Lisa, what she just showed us, all those habitat models, they're really informative for identifying indicators. So the strength of the coefficients in those models can tell us how sensitive they are to change in habitat. In this case, we might need to put pumpkins into the FRI since some wildlife seem to like pumpkins. So thresholds, this is another thing that's useful in, it's really useful in linking management and monitoring, right? Thresholds, ecological thresholds can tell us where you have a small change in forest condition that we might manage and you have a large change in a wildlife response. It suggests like something that may be a meaningful threshold, in this case, where we look at nonlinear relationships in the models Lisa did. And so that helps you kind of find that balance between forest management objectives and biodiversity objectives, right? Where you want to know how much you can harvest before it's going to have a negative impact on species X, Y, Z. So these kinds of thresholds can be quite intuitive and useful that way. And it suggests a sensitivity that we are interested in using to help us identify useful indicator species. So this data is for caribou in their response to roads and too much mixed forest where they like more of a mature, pure conifer stand. We've got other examples, right, from our MSIM data analysis. The models Lisa just showed, the links where their occupancy drops way down when there's a certain threshold point of harvest in the landscape. So that's at a big landscape context, but even at that finer scale of stands and individual trees within the stand, characterization for a species like the brown creeper, this bird nests in the bark of big trees, so it likes mature trees, and we see within our data that there's this kind of threshold response where it's only found in stands where tree height, so that characterizing these big mature trees where it can use to nest, are beyond a certain amount. So this can help us kind of inform and interpret our trends in wildlife by then going back to our ground data and our FRI to see what might be driving that change and whether forest management is relevant at all, right? So yeah, we're kind of interested then in looking at all these models that Lisa's been producing and then summarizing up, well, how prevalent are thresholds really in these wildlife communities? And maybe, there are quite a few, as you see. This is what we found so far in terms of mammals and birds, where there's quite a few that show these nonlinear threshold style responses that we can use then to identify indicators, and that'll be useful for identifying habitat targets within our reporting framework for the wildlife and habitat kind of parts of the program. So again, a work in progress. Samantha's got to kind of put all this together and compare methodologies, not focus just on one, and look for robustness and consistency amongst these methodologies, I think, for us to pick useful indicators. I'm going to skip that. So yeah, just to kind of wrap up, I think we learned from the project that, FRI is useful. It came up, FRI-derived variables came up quite a bit in our habitat models, but I think it was important for us to go beyond that, right? Like that's the main management lever we have, but it's important, I think, when we're interpreting trends in wildlife to not assume. Like if we just looked at the forest condition response, yeah, you may find a relationship, but there are other drivers for wildlife, right? Both, not only just in the understory and the overstory situation, but climate, there are prey and things, and some of those things we don't monitor, some we do in the ministry, especially as we move in the ministry towards more, like there's the integrated monitoring framework of combining different monitoring programs and looking for efficiencies. And so there may be room there to cast like our models, and it was important for us to kind of have that hypothesis-driven framework of other variables so that we can better interpret trends to know whether management response through forestry is appropriate or not. So it puts us in a better position, I think, to make decisions. And so that suite of information, I think we can use it for evaluating those models, in particular for evaluating management options within FMPs, but also they can be directly used within the the science packages within the forest guides when future updates come into play for that. And the information is going to go a long way, I think, for the wildlife assessment program for its typical reporting, like putting information into the state of the forest report. So that's it. Yeah, that was from one of our MSIM cameras. Yeah.
When you were looking at the FRI data in relation to habitat, did you factor in the ELC component that came with the FRI?
No, and I was thinking about that yesterday when like, well, maybe when I was talking to Lisa, like the moss thing she showed for one of her models, right, for food, and I thought, we could probably get that out of the ELC without using our ground data where, I'll admit, right, the analysis where we did it, it was a limited data set. Like you guys have a much bigger ground data set where you could strengthen your models for some of these inferences we've been talking about doing. And I think just the ELC alone, all the history of work that's been already done there, we could probably go back to that and take our models where things like ground variables like moss come up and then look at the ELC and say, well, which of those community types in that range we already know with confidence have more moss in them. So yeah, I think that's a great idea. We didn't look at it, unfortunately, but I think moving forward we should.
Dr. Glen, Lisa, thank you very much.